Welcome to the fifth lecture on factorial experiment. So, you may recall that in the earlier lectures what we have done, we started a discussion from a very basic framework of 2 square factorial experiment, where we had 2 factors and each of the factor were at 2 level. So, we took that example. From that example, we had done different types of manipulations to understand that how different type of terminologies which are used in the factorial experiment, like as mean effect, interaction effect, general mean effect, etc., have been evolved. Through that example, I tried my best to explain you that how the concepts of simple average, difference, addition, etc., they have been used, or how the different treatment combinations have been used to compute different types of effects in a factorial experiment. Using that example, I extended it to formulate the basic theory, basic notations, and most of the things in a more formal way. So, using an informal example, I have tried to develop the formal theory of the factorial experiment. Then in the last lecture, I took an example of say 2 square factorial experiment, 2 cube factorial experiment, to give you an idea that how the things are being extended from a statistical perspective to a mechanical perspective. What do you mean by mechanical perspective? For example, you have found that how to find out the main effect A and B in a 2 square factorial experiment, but that was extended mechanically in the sense that I ask you that if there are 2 factors A and B, you have to write them in the format of A minus 1, A plus 1, B minus 1, B plus 1, depending on which factor is present, which letter is common between the capital letters, which are the effect, and the small letters, which are the treatment combinations. So, in 2 square factorial experiment, I did everything. Then in the 2 cube factorial experiment, I use them mechanically. Now, in this lecture, I am going to take a most general framework, that is 2 raised to the power of n factorial experiment. That means, there are not 1, not 2, not 3, but there are n factors, and each of the factor is at 2 levels. So, under this type of situation, how are you going to express main effect, interaction effects, how are you going to express them in the form of a linear contrast, how you are going to compute the different sum of squares, and finally, how are you going to obtain the different types of test statistics for testing various types of null hypothesis. So, that is what I am going to do in this lecture. So, let us start our discussion from this slide. So, now in this 2 raised power of n factorial experiment, you know there are going to be n factors, and each factor is at 2 levels, levels 1 and say here level 2. And as per the rules of factorial experiment, these n factors are going to be represented by capital letters. So, all these capital letters, capital A, capital B, capital C, etc., they are going to denote the factors. And once we have these factors, then we have different types of effects. One is the main effects, and say another are interaction effects. For example, you have seen that in the case of 2 square factorial experiment, we had 2 main effects A and B and 1 interaction effect A B. Similarly, in the case of 2q factorial experiment, there were 3 main effects A, B, C, and there were 4 interaction effect A, B, B, C, A, C and A, B, C. So, now you can see here from these 2 examples of 2 square and 2q factorial experiment that the interactions can be something like A, B, C and so on. So, if we have some higher order factorial, possibly those interaction can be A, B, C, A, B, C, D and so on. So, whenever we are trying to use 2 letters, that is interaction like A, B, interaction like A, C, interaction like B, C, then they are called as first order interaction. There is another terminology and we call this first order interaction also as 2 factor interactions. 2 factor means there are 2 factors like as A and B or B and C and so on. Similarly, when we are trying to take 3 letters at a time like as A, B, C, A, B, D, B, C, D, etc., then they are called as second order interactions, or they are called as alternatively as 3 factor interactions. So, this is how we try to define this first order, second order interaction or 2 factor interaction, 3 factor interactions and so on. And you have to keep in mind that once you are using the terminology order interaction like as first order, second order. So, first order has 2 letters whereas second order has 3 letters. On the other hand, if you are using the terminology like 2 factor, 3 factor interactions, then 2 factor mean there are 2 factors, 3 factor mean there are 3 factors. We also had seen in the case of 2 square and 2 square and 2q factorial experiments that each of the main effect and interaction effect degrees of freedom, and in the sense that the sum of squares of that effect, this follows a chi-square distribution with 1 degrees of freedom under normality of y, that is the response variable. So, in the case of 2 to the power of n factorial experiment, you can see that there are going to be total number of main effect equal to n choose 1. Means earlier in some books we used to write like nc1, which is equal to here n. So, that is obvious if you try to see here in the case of 2 square factorial experiment, there were 2 main effects like as A and B. In 2q factorial experiment, there were 3 main effects A, B and C. Similarly, if you go for the first order interaction or if you try to count the 2 factor interaction, this number is going to be n choose 2, right. For example, if you try to see here in the case of see here 2 square factorial experiment, the interaction was A B, and in the case of 2q factorial experiment, the interaction were A B, B C and A C. They were the first order interaction or 2 factor interaction. Similarly, if you try to count the total number of second order interaction or 3 factor interaction, they are n choose 3 and so on. For example, if you try to take the example of this 2q factorial experiment, then in this case the interaction effect was ABC, because was the only 3 factor interaction. And similarly, if you try to increase the order of the factorial like s to the power of 4, so there are going to be 4 main affect A B C D. There are going to be 2 factor interaction like A B, B C, A C and so on. There are going to be 3 factor interaction A B C, B C D and so on, and there is going to be 4 factor interaction as A B C D. Right. Now, we try to define some basic definitions which are used in this factorial experiment in the case of a factorial experiment as well as in the next topic on confounding. This is called standard order for the treatment combinations. The list of treatments can be expressed in a standard order. What is this list of treatments? For example, if you remember in the case of 2 square factorial experiment, we had 4 treatment combination 1 A B, and similarly in the case of 2q factorial experiment, we had 1 A B C, A B, B C, A C and A B C. So, these are my treatment combination in 2 square and 2q factorial experiment. So, now these treatment combinations, they have to be expressed in a particular order. What is this order? For example, if there is only one factor, then we will write the treatment combinations like as in this order: 1 and then A, like as A here. So, this is called the standard order of one factor A. Similarly, if I want to write down the standard order for the one factor B, then this is going to be 1 B. Now, in case if I try to take 2 factors, say A and B, then first question is how we are going to obtain the standard order. So, the rule is very simple. First you try to see, I am going to write in green color. In case if you want to obtain the standard order for the 2 factors, the rule is this: you start with the first factor. So, first factor here is, and then go alphabetically. Because the first factor according to the rules of alphabet is A, whose standard order is given by 1A. Now, you try to take second factor B, the standard order, and try to write down the standard order of the factor B, like as here 1B. Now, just for a while you try to assume that these are some mathematical quantities, and you try to multiply 1 and A by this standard order of B in the following way: that you first try to write 1A and multiply it by here 1, and then you try to write down 1A and then you try to multiply it by here B. So, you can see here this will come here, 1 into 1 is 1, 1 into A is A, 1 into B is here B, and A into B here is AB. Well, one thing you have to keep in mind, this is not really a mathematical thing, but this is one of the way by which we can obtain the standard order. You have to treat this non-mathematical quantities discussed for a while as a mathematical quantities. So, you can see here, this is how I have obtained here the standard order of 2 factors. Now, similarly, if I want to obtain the standard order for the 3 factors, so what I have to do? I already have obtained the standard order for two factors, which was 1 a, b and ab. My third factor is c, and the standard order of c is 1 and c. Now, what we try to do here, I have to write down the standard order for the two factors, and I have to multiply it by here the standard order of the third factor c. So, you can see here, once you are trying to multiply this a b by here 1, and then 1 a b into c. So, this is now here 1, a into 1 is a, b into 1 is b, ab into 1 is ab. Now, I try to multiply this c by here 1. So, 1 into c is c, and then next thing a into c. So, this is ac, then next component bc, and then abc. So, this is my standard order, and in a simple way I can say that if you want to find out the standard order of the three factors, and if you already have found the standard order of the two factor, so the rule is this: first you try to write down the standard order of the two factors, which I am going to denote here in the red color, and then whatever is this order, you try to multiply it by here c, like here like this, and then whatever you will get, that will be the standard order for the three factors, right. And yeah, means if you want to go for 2 raised power of 4 factorial experiment, what you have to do, you simply have to write down the standard order for the three factors that you already have obtained, and then just multiply it by here d with this thing, and then you will get here 1 a b a c and so on here. This I am making a circle. This you will get as the standard order for the 4 factors. So, this is how you obtain the standard order, right. So, now I come to the next aspect. In order to find out the sum of squares, first you need to compute those factors. So, you can recall that earlier we had considered the 2 square factorial experiment, in which we had computed the main effect a, for example, as here like this, and this component has this expression has 2 components. One is here this multiplication factor or the divisor, which is here 2, and another here is the expression a minus 1 into b plus 1, and and similarly in the case of ab also, you have here divisor 2, and the expression here is a minus 1 and b minus 1. And if you try to expand it, you will get here expressions like this one. For a, this will be 1 by 2 minus 1 plus a minus b plus ab, and for the ab, this will be 1 minus a minus b plus ab. So, now I will show you that when you are trying to consider the higher order factorial experiment, how you can write such a thing, and for that you need not to do the type of manipulations, and or you need not to understand the type of explanation that we had considered in case of 2 square factorial experiment. So, I will try to give this expression for the general 2n factorial experiment. So, in the First part, I try to consider how to write down the divisor. So, we had seen that when we had considered the 2 square factorial experiment, then all the factors a, b and ab, this has the multiplication or the divisor here 2, whereas for the general mean effect the factor was 1 over 4. So, similarly, when we are trying to write down the expression for 2 raised to the power of n factorial experiment, there are going to be 2 types of component. One is here general mean effect, and second category will be all the effect like as main effect or any interaction effect. So, the rule here is very simple now for you. For the general mean effect, the divisor is going to be 2 raised to the power of n, and for all other main effect and interaction effect, the divisor is going to be 2 raised to the power of here n minus 1. And now you can recall here, when you were trying to consider the 2 square factorial experiment, then for a, b and ab, the divisor was 1 over 2 raised to the power of 2 minus 1, which is equal to here 1 upon 2, and for the general mean effect this was 1 upon 2 square, which was 1 over 4. Similarly, when you considered the 2 cube factorial experiment, then for all the effect a, b, c, a, b, b, c, a, c and a, b, c, your divisor was 1 over 2 raised to the power of 3 minus 1, which was here 1 over 4, and for general mean effect the divisor was 1 over 2 power of a cube 1 upon 2 cube, which is here 1 upon 8. One thing what you have to understand here, that this divisor what I am telling you here mechanically here as say 4 or here 8 or here 2 or here 4, this is not actually divisor, but that is coming because you were trying to compute the main effect or the interaction effect by taking different types of combinations. So, this divisor is not really a divisor, but that divisor is originating because of those concepts which may not look clearly here from this expression. So, this is what you have to keep in mind, and that was my objective when I had explained you that how you are going to get those expressions. Now, you can communicate from the first lecture to this lecture, and you can understand that how these divisors are coming into picture. So, similarly, just for the sake of an example, if you are trying to consider a 2 to the power of 6 factorial experiment, now you can imagine that it is very difficult to write down those different types of averages to decide how you can compute the main effect or how you can compute the interaction effect. So, in this case this mechanical rule will help us, and whenever we want to write down the divisor for the general mean effect, this will be 2 to the power of 6, and for any other main effect or interaction effect, this divisor is going to be 2 to the power of 6 minus 1, which is equal to 2 to the power of 5. And obviously, all these divisors I had shown you that they are based that we have only one observation. In case if I am trying to repeat the observation and suppose we have r replicates, then this divisor is going to be multiplied by the r, because then the average will be based on each of those r replicates also. So, in case of general mean effect, in case of a 2 to the power of n factorial experiment, the divisor is going to be r into 2 to the power of n, something like 1 over r into 2 to the power of here n, and for any other main effect or say interaction effect, this divisor is going to be 1 over r 2 to the power of n minus 1. So, this is how you can write down the divisor. Now, I explain you how you are trying to how will you write the expression. So, in order to write down the expression, first you have to recall your earlier 2 lectures, when I considered the 2 square factorial experiment and when I considered the 2 cube factorial experiment. I had given you all those expressions, and using some artificially I had expressed those linear combinations in the form of a minus 1, b plus 1, a plus 1, b minus 1 and so on. So, essentially I had 4 terms, a minus 1, a plus 1, b minus 1, b plus 1, and I have taken a different combinations to express the different types of factors and interaction effect. For example, I had told you that if you want to write down the main effect of A, then you have to simply see on the left hand side and right hand side, whichever letter is common, that will appear with minus sign, and that letter which is absent, that will appear with plus sign. For example, if I want to write down the main effect of A, then that is going to be A minus 1 into B plus 1. And similarly, if I want to write A B, then this is going to be A minus 1 into B minus 1. And similarly, I had explained you this rule in a more mechanical fashion in case of 2q factorial experiment. But now I am going to extend it to a general case to the 2 to the power of n factorial experiment. So, what I am going to say here, suppose I have say factors capital A, capital B, capital C up to say capital Z, and I have to write down the main effect, 2 factor interaction, 3 factor interaction and so on, and the highest order interaction will be A into B into C up to here Z. So, by this by those 2 examples means I would like to extend the theory and concept that were developed earlier into this to the power of n factorial experiment. So, let us try to concentrate here in this slide. So, you can see here that I have taken here factors A, B, C up to here Z. Now, obviously, this is 2 to the power of n factorial. So, this is going to so the factor A has 2 levels 1 and A, factor B has 2 levels 1 and B and so on, and factor Z has 2 levels 1 and say here Z. So, now you can see here when I want to write down here A, then I have to write down A 1, B 1, C 1 up to here Z 1. Now, in the next step I have to choose what should be the sign plus or minus here. So, the rule is very simple. If you try to see on the left hand side of this equality sign, this is here A, and on the right hand side this is here A. So, in this case this is going to have a negative sign. On the right hand side there is here B, but there is no B here on the right hand on the left hand side of equality sign. So, this will appear as say here B, and similarly here C will appear here with plus 1 sign and Z will appear here with plus 1 sign. So, let me take here one more example. Suppose I want to write down here A, B, C and here D. So, first I will try to write down A 1, B 1, C 1, D 1 up to here say here Z 1. Now, I have to see what is matching and how are we going to use it. So, you can see here there are 4 letters A, B, C and D on the left hand side of this equality sign. So, now I have to use minus sign with A, B, C and D, and after that if I write here E, this will be E plus 1, F plus 1, G plus 1 up to here Z plus 1, right, and exactly this is what I have written here. For the A, you can compare this expression and this expression. Similarly, for the B, the corresponding negative sign will occur with B minus 1 and all other factors will have plus 1 sign. Similarly, if you try to take here A B, A and B has 2 points common. So, A and B will be with minus sign, and all other factors c plus 1, d plus 1 up to z plus 1, they will occur with plus 1 sign. And finally, if you come to ABC up to z, all the factors on the left hand side and right hand side are there. So, everything will appear with minus sign here, this you can see. And now, after this, once you write this expression, you simply have to expand it, right. For example, you have to just expand it mathematically, what you try to do, and then combining these expressions and the divisor, you will get the final outcome. And you can see here that these things, they can be expressed as a function L transpose y, but I will try to discuss it in more detail after a couple of minutes. So, just for the sake of simplicity, I am now showing you here that in case of 2q factorial experiment, I had obtained the divisor of the main effect A as 1 upon 2 raised to the power of 3 minus 1, and with here A, this is here with positive sign, and B and C, they are occurring with, sorry, A is with negative sign and B and C are occurring with positive sign. And if you try to expand it, just assuming it to be a mathematical expression, just like a mathematical expression, you will get this complete expression. And the same thing occurs with the general mean effect here M. Here the divisor is going to be 1 upon 2q, and all those factors will appear here with plus sign ABC, and if you try to expand it, you will get here this expression, which is the general mean effect in case of 2q factorial experiments, right. So, that is the same thing what you had obtained here, but now I have shown you with some mechanical aspect. Here I would like to make a comment. Well, given the time frame what I have, I am considering here one approach. If you try to go through with the book, there are some more approaches. So, I am not saying here at all that you have to use only this particular approach, but you can use any of the approach which is correct. That is the only condition. It has to be correct, and it should have a statistical background. Whatever I have told you, although it looks mechanical, but this has got a strong statistical background. So, you are free to use any of those correct approaches, right. Now, next thing I comes, now you have computed the main effect and interaction effects. Now, the next aspect is how to compute the sum of squares. So, for that, if you try to consider the 2n factorial experiment, and suppose this is carried out in randomized block design with R replicates. And you may recall that I have repeated this sentence couple of times during these lectures, that factorial experiments are always conducted inside the block design. That can be randomized block design, that can be Latin squared design, that can be balanced incomplete block design, or this can be any type of block design. So, now what are we going to do? That whatever is the outcome, that will be denoted by here the letter here y. And what does this mean? That we have here different types of plots in which we will try to give different types of treatment combination, and every treatment combination will be repeated small. So, altogether there will be R plots, or there will be R experimental units which will be receiving a particular treatment combination, right. So, whatever is the total yield from that treatment combination, that is going to be denoted by here square brackets. For example, if there is a treatment combination here A B which is given to this plot, this is given to here this plot, this is given to here this plot, this is plot number 1, plot number 2, plot number here R. So, I will be getting here all the outcomes from first plot, second plot, R plot. So, this A B is so small is if I write to die small a b inside the square bracket, then this a b denotes the total yield from the plot receiving the treatment combination a b. So, this is going to be some numerical value, right. So, whenever we are trying to write a value inside the square bracket, that means it is some numerical value. So, yeah, for example, if you try to see in the case of 2 square factorial experiment, this a was given out to be here a b minus here b plus a minus here 1. But now I am trying to write down here say square bracket, and then inside the square bracket I am writing here a, and similarly here inside the square bracket here I am trying to write down this treatment combination. So, this square bracket a b, that is denoting the treatment total, that is the sum of r observation in which both the factors a and b are at the second level. And similarly, this a is here what? That means a is at the lower level and b is at the A is at the higher level and B is at the lower level. So, this is going to denote the treatment total, that is the sum of R observation in which the factor A is at the second level and factor B is at the first level. And similarly here small b inside the square bracket b and 1 inside the square bracket, they are also going to denote the treatment totals or the sum of observation when those treatment combination have been assigned to all the plots, right. So, now in case if you try to see, suppose I say that for a particular plot, this total yield is going to be this A is going to be computed here like this. Then the total yield, that will be the sum of all the plots, say plot here 1 plus from plot 2 up to here, see here plot R, right. So, this is what I am denoting here, and this expression can be written also as say here y a b for the ith observation minus y b, that means the output y when the treatment b is given at the I level, plus y a, that means the output when the treatment combination A is given at the ith level, and here minus here 1 when both A and B are at the 0 level, and this is the ith observation. So, I am going to sum here all the observation, and whatever is this thing you can see here, this part, this can be expressed as some L transpose here y, and say for the ith observation. And we already have discussed that this L is going to be a vector comprising of 2 plus 1s and 2 minus 1s. And now this thing is going to be repeated again and again, and whatever is the outcome, that is also again going to be a linear combination. Why? Because the linear combination of linear combination is also a linear combination. So, this can be expressed as a L transpose A y, and you can see here that this linear combination is a contrast. So, this is also going to be a contrast. So, the message is very clear that when you are trying to compute say any factor or interaction effect from the R replicates, even then they are estimated as a linear contrast, right. So, I have given you an example of here A, and but similarly you can obtain the different types of say this linear function for computing the main effect B, C or interaction effect A, B. The only difference is going to be that this vector L will be changing. For B, this may have a different combination, for A, B, this may have a different placement of plus 1 and minus 1 in that vector, right. Once you have obtained this estimate in the form of L transpose y, then the sum of squares due to any particular effect, they are obtained as say here as a total yield whole square divided by the total number of observation. So, that is simply going to be the here L transpose y, the entire function whole square divided by the total number of observations. So, for example, in case of 2 square factorial experiment, this is the sum of square due to factor A, this is L transpose A y A whole square divided by 2 square multiplied by here R. And similarly, in case if you are trying to consider here a 2n factorial experiment, then this 2n factorial experiment, when it is conducted inside an RBD, then the divisor is going to be R into 2 to the power of here n. Right. Do not get confused with the divisor which is here in the sum of squares and the divisor which was in the computation of main effect and interaction effect. Right. Now, I would try to show you one very interesting thing, and this will indicate you why this factorial experiment is useful. So, I will try to take an example of 2 square factorial experiment, and I will write down the analysis of variance which you obtain from an RBD when there is no factorial experiment used. And then I will show you that when you try to use the factorial experiment inside the randomized block design, then how the analysis of variance changes and how do you get the different type of result, or what will be the difference in the outcome when you are trying to use factorial experiment and when you are not using the factorial experiment in the same block design, that is randomized block design. So, you very well remember that how the analysis of variance in the case of randomized block design used to look like. So, in this slide I have just taken that ANOVA table, and from this ANOVA table I will try to show you that how the things are happening, right. So, you may recall that in the case of RBD there were 2 factors which was block effect, treatment effect, or we are calling here as a due to replication or due to treatment. And you remember the degrees of freedom, if there are say here B blocks, then the degrees of freedom associated with the sum of square due to blocks was B minus 1, and if there were V treatments, then the degrees of freedom associated with the sum of square due to treatment were V minus 1. Right. Now, in this case, how many treatments we have? Suppose if I try to take the example of 2 square factorial experiment. So, that will be here A, B, AB and M, that is the general mean effect. So, here V is equal to here 4, right, and B here I am going to take it here as a R, which is the number of replication. So, when I was earlier constructing the ANOVA table, then I was simply writing due to replication the degrees of freedom are the degrees of freedom associated with the sum of square due to block were R minus 1 or earlier as say B minus 1, and the degrees of freedom associated with the sum of square due to treatment, they were V minus 1 or 4 minus 1, which is equal to here 3. And after this I was trying to write down here the sum of square due to block, sum of square due to treatment, and then based on that I will try to define here f statistics using the sum of squares due to error. Right, and then one thing you have to keep in mind for the case of sum of square due to total and error, there is the degrees of freedom are the same, there is no change. Now, let me show you here that what change is now occurring. So, now I am trying to say here there are 3 degrees of freedom, and now I am trying to divide these 3 degrees of freedom into 3 components, 1, 1 and here 1. So, essentially if you try to see you have extended the concept of analysis of variance, that the total variation has to be partitioned into different different orthogonal components to this sum of square due to treatment also. And corresponding to sum of square due to treatment, you are trying to write down here as a sum of square due to A, sum of square due to B, and sum of square due to AB. So, essentially the earlier, when you were trying to decompose the total sum of squares into SS block plus sum of square due to treatment and plus SSE. Now, you are trying to further decompose this sum of square due to treatments into SSA plus SSB plus here SSAB. And earlier you were having only one F statistics which was trying to compare all the factors, but now you have here three different F statistics for A, B and here AB. So, you can test the significance of individual components, that is factor A, factor B and interaction AB. So, now you can see here that these three different degrees of freedom are divided into three different mutually orthogonal components, and the corresponding sum of squares, they are obtained here like this. Sum of square due to A is here like this obtained, sum of square due to B, this is obtained here like this, sum of square due to AB here is obtained here like this. And means after this, there is going to be SSE and there is going to be here TSS, and based on that you can define the F statistics, say for example SSA upon SSE divided by degrees of freedom, error and so on. So, this is for here F A. Similarly, you can define here SSB, the F statistics for B, that is SSB divided by degrees of freedom, SSE divided by degrees of freedom, and here FAB, which is equal to here SSAB divided by degrees of freedom 1 divided by here SSC divided by degrees of freedom. So, this degree of freedom here is 3 times r minus 1. So, now after this you can conduct the analysis of variance exactly in the same way as you used to do earlier, and the decision rule to reject the concerned null hypothesis when the related computed F statistics, that is F of effect, is greater than the tabulated value of F statistics from the table. Now, you have seen what I have done and why I was trying to emphasize on the utility of factorial experiment. One approach which you have to observe here, that instead of first considering the 2 raised power of n factorial experiment and then trying to give the different example of 2 square or 2q factorial experiment, I have gone in the opposite way. Means I have taken the examples 2 square, 2 cube, etc., and from there I have tried to construct the theory for the 2 raised power of n factorial experiment. So, my idea was that first let me introduce you with the basic concept, and the most simple concept I could construct was from the 2 square factorial experiment, where given my sheet, given my slide, given my blackboard, I can easily explain you that how this factors, main effect, etc., are computed, because initially it looks very strange that you have only 4 observations, one on A, one on A, one on 1, that is the 0 0 level, one on A, one on B and one on AB treatment combination. Just using 4 combinations you can compute the general mean effect, you can compute the main effect of A, you can compute the main effect of B, as well as you can compute the interaction effect of AB. Similarly, in case of 2q factorial experiment, you have only 8 observations, and using those 8 observations only in a different way. Sometimes you are adding some other observations, you are subtracting some other observations, and just by taking the different type of linear combinations such that the linear combination are contrast, you can compute the main effects of A, B, C. You can compute the 2-factor interaction A, B, B, C, A, C. You can compute the 3-factor interaction A, B, C, as well as the general mean effect. So, using only 8 observations, you are trying to compute 8 different quantities, which sometimes becomes very difficult for a student to understand that how this is happening. Once he is convinced that okay, this is happening, the student will always like to know what is the statistical background, what is the statistical concept behind it. Sometimes people have a confusion that that everything is happening mechanically. So, you will find many students who can find out all these things mechanically, but they may not really understand what is really the basic theoretical foundation or what are the statistical concepts which are being used in this analysis. So, that was my objective, that I try to convince you that why a particular combination of those 4 observation or 8 observation is going to compute the main effect of A or main effect of B or the interaction effect A B. And then I also try to convince you that why the divisor is sometime 2, sometime 4, sometime 8. This divisor ultimately that is coming from a mechanical rule, but this also has a logical interpretation which is based on certain concepts. And once you have learned that how to compute these different types of main effects and interaction effect, then I had shown you that how to compute the sum of squares. Once you have obtained the sum of squares, then you can compute the mean squares, and then you can find out the corresponding of statistics. The second aspect which I was trying to explain, that what really happens if you try to conduct a block design without factorial experiment. So, for that I have taken the example of randomized block design, and where I have given the example of 2-square factorial experiment, and I had shown you that what difference or what impact will come when you try to use the factorial experiment inside this randomized block design. So, you can see, means earlier all the treatment effect, they were just filled in one basket, and the basket is closed. But now what is happening? The basket is open, and you know the effect of each and every factor and interaction effect. So, that will help you in going into the minor details, whether this factor is more important or this interaction effect is more important, which factor is contributing, which factor is not contributing, which are the factors and interactions which have got the same effect. But this can be done through the use of factorial experiment. Without using them, you cannot find it out. So, this is the utility and use of factorial experiment. So, we stop with this factorial experiment and see you in the next lecture with a new topic. Till then, goodbye.